first. Last week we started this chapter already, but I will start from the beginning to have a review first. In this chapter, we are going to cover the second law of thermodynamics and learn what entropy is. As we remember, the thermodynamics has three laws: the first law, the second law, and the third law. The first law of thermodynamics deals with the conservation of energy, or in other words, it deals with the quantity of energy. On the other hand, the second law of thermodynamics deals with the quality of energy. So, a statement of second law is the thermodynamic processes occur in one specific direction, not in any direction. For instance, heat energy is transferred from high temperature to low temperature by itself spontaneously, but never in the opposite direction. So in order to move heat from lower temperature to higher temperature, it's necessary to provide additional energy, and this is what happens in refrigerators actually. If you look at the figure here, a container with some pressure in it has a valve at the top of it. When the valve is opened, the pressurized air exits the container until the pressure inside the container and outside the container becomes equal. In this case, you can see that energy contained within the container is just wasted because it's just an expansion of air. However, some part of it could have been converted to work. For instance, if we have installed a turbine here, so during the expansion of the air, some work could have been obtained. So what is the amount of work that is obtained or that can be obtained? So the second law decides the theoretical maximum of the work that can be obtained and the factors that would affect the amount of work that could be obtained. The second law provides means for the direction. So it says the processes have certain directions, not just any direction. It's always from high temperature to low temperature, the heat energy flow, or high pressure to low pressure, the fluid flow, or electric current from high voltage to low voltage, and so forth. Also, by using the second law, we will determine the conditions for equilibrium, thermal equilibrium. We will calculate the theoretical performance of the cycle, which is the highest possible theoretical cycle. So this is going to be taken as a reference, and we will say that no real system, no actual system can have a better performance than this theoretical performance. Then we will quantitatively calculate the factors that affect the performance. When we say performance, of course, we are mentioning efficiency in heat engines and of performance in refrigerators. Then we will be using temperature scales in ideal cases or in theoretical cases, which is the Kelvin scale. The importance of Kelvin scale is shown in the use of theoretical systems. So we will be using temperature scales, which is Kelvin scale, in order to determine the performance of the systems. Then we will also evaluate the properties such as internal energy and enthalpy by using the second law definitions that we will see in this chapter. So let's remember from last week what was a thermal reservoir. A thermal reservoir is a special kind of system which has always a constant temperature, no matter how much heat is added or how much heat is removed. For instance, atmosphere or sea or large lakes are thermal reservoirs because no matter how much, for instance, hot water you put into sea, you cannot change its temperature. Or no matter how big a fire is, you cannot change the temperature of the atmosphere. So these systems are called reservoirs, thermal reservoirs, meaning that they have always constant temperatures regardless of the heat and added or heat removed. We have two statements explaining the second law. One of them is Clausius statement, the other is Kelvin-Planck statement. Clausius statement is related to refrigerators, and it says that it's impossible for any system to operate in such a way that the sole result will be an energy transfer by heat from a cooler to a hotter body. So it just says that unless there is an external provision of energy, it's not possible to transfer energy from cold reservoir to hot reservoir. This happens in an refrigerator. In a refrigerator, as you know, you remove heat from inside the refrigerator, which is colder than the outside. So inside is the low temperature reservoir, outside is the high temperature reservoir. Outside can be the kitchen, while inside is the low temperature reservoir. So in order to remove heat from the low temperature reservoir and to transfer it to high temperature reservoir, which means to the kitchen, it's necessary to provide external energy, which is the energy by the compressor of the refrigerator. So this is what the Clausius statement says. The second statement related to the second law is Kelvin-Planck statement. Kelvin-Planck statement is about the heat engines. So Clausius statement is about refrigerators, but Kelvin-Planck statement is related to heat engines. According to Kelvin-Planck statement, it's not possible to convert all the energy delivered to a system to work in full. So it says that there is no possibility to have a heat engine with 100% efficiency, because we have to reject some energy so that the cycle can repeat itself. Without rejecting some of the heat, a cycle cannot be continuous. So according to the Kelvin-Planck statement, it's not possible to convert all the input energy to work. The maximum efficiency or the maximum performance of a system is limited by the existing of irreversibilities. A reversible system is a system that can return to its original system, that can restore to an original system. For instance, consider a pendulum without any friction. So a pendulum without any friction, no friction at the connection, no friction with the air, will indefinitely oscillate because there is no irreversibilities between the pendulum and the surroundings. So in this case, the motion of the pendulum is infinite. But in real systems, there are always some kind of irreversibilities. For instance, heat transfer through a finite temperature difference. So heat loss from a wall of a house is an irreversibility. Unstrained expansion, such as the expansion shown in the figure here. So this is just an unstrained expansion. By having such an unstrained expansion, some of the work capability is just lost. So this is a kind of irreversibility. Spontaneous chemical reaction. Once a chemical reaction is realized, it may not be reversed exactly the way it was. For instance, hydrogen and oxygen is combined to create water, but water cannot be reversed back to the hydrogen and oxygen without adding external energy. So this is a sort of irreversibility. Spontaneous mixing of matter. So once some metals are mixed, they cannot be separated without external effects. Friction. Friction is converted to heat. It can be solid to solid friction, solid to fluid friction, or internal fluid friction. And once this friction is converted to heat, then it's not possible to convert the heat back to the useful work. So this is another kind of irreversibility. Electric current. Electric current is converted to heat when it flows through a resistance, but if you hit the resistance, you cannot obtain electric current. So this is another irreversibility. And magnetization or polarization or inelastic deformation are other kinds of irreversibilities. So in real life, there are always some irreversibilities associated with the systems, and they reduce the performance of the systems. The existence of the irreversibilities reduce the effectiveness or performance of the systems. We will see the use of the term of irreversibility in the calculation of system performances. Irreversibilities can be of two types. There can be irreversibilities within a system. For instance, a turbine can have a irreversibility within it as fluid friction between the turbine blades and the fluid itself. And it can also external irreversibilities, such as it can lose some heat to the surrounding. So the sum of the internal and external irreversibilities will give you the total irreversibility. If it's only reversible internally, it's called internally reversible. Or if it's completely irreversible, meaning that there are no irreversibilities within the system, and with the system and the surrounding, it's called complete or full or uh, completely reversible. In the solution of physics problems like mechanics, we assume uh, some non-existence of irreversibilities to be able to solve the problem with ease. For instance, in mechanics, you remember that we take the masses as point masses, just a small point, or we assume the pulleys to be frictionless, or the beams to be rigid, and so forth. The reason why we take them as irreversible systems is because otherwise the solution would be very difficult, especially by hand solutions. So once we have a solution by the assumption of reversibilities without the existence of irreversibilities, we can use some factors called efficiencies or correction factors to estimate the actual performance of a system. So we start with the highest possible efficiency calculation. assuming that system is completely reversible, then we can define some factors called efficiency or correction factors to determine the actual performance of the system. Remember, in a heat engine, we have two reservoirs, one of them a high temperature reservoir and the other one is a cold temperature reservoir. As the heat is transferred from high temperature reservoir to cold temperature reservoir, it's possible to convert some of the energy that's added in the high temperature reservoir to be converted to heat to work. So this is similar to the conversion of energy in a steam plant. Remember that in a steam plant there was a pump which pumps liquid water to boiler. Boiler converts the water to steam, and the steam is sent to a turbine in which work is obtained. And because the exit of the steam is also vapor but at low pressure, it has to be converted to liquid so that it can be pumped back to the boiler again. So in this case, you can see that boiler is the high temperature reservoir here, and the condenser is the low temperature reservoir, whereas the turbine is where we get the work. Only a small portion of the turbine energy is input to the pump, but it can be neglected for most of the times because the magnitude of the pump work is much less than 1% of the magnitude of the turbine work. So as you can see, it's necessary to convert to saturated liquid, saturated vapor, leaving the turbine to liquid. Otherwise, it's not possible to pump it back to the boiler. So as you can see, without the existence of this heat rejection or heat loss, it's not possible to have a continuous cycle. So according to the second law, we have to have a heat rejection for completing the cycle. This is from the Clausius statement. So by having these definitions, by saying that some of the work, some of the input energy is converted to work, we can calculate the efficiency as output divided by input. Output is the network of the system. Network is turbine work minus pump work divided by the input, and input is the heat added in the high temperature reservoir. So the efficiency of this system is turbine work divided by the boiler heat. And it can never be 1 because not all the heat energy can be converted to work. So it's always less than 1. And as a matter of fact, it's most of the time much less than 1. For instance, for a system such as this one, the efficiency is around 30%. For an internal combustion engine, it could be as high as 40%. For a gas turbine, it could be as high as 50%, and so forth. For a fuel cell, for instance, the efficiency of a fuel cell can be as high as 70%, but it never gets closer to 1 because of the fact that there is a necessity for some heat rejection. Otherwise, the cycle cannot be completed. The systems without any irreversibilities or completely reversible systems are called Carnot systems. We have two types of Carnot systems. The first of them is Carnot heat engine. The other is Carnot refrigerator. So let's take a look at the Carnot engine. it says that the thermal efficiency of a irreversible power cycle, which is the actual power cycle, is always less than the thermal efficiency of a reversible power cycle, which is the Carnot cycle. So we have a situation in which the efficiency of an actual system is always less than the reversible system. Well, I will tell you why I used S here. It represents the reversible system without any reversibilities. And we always have a situation in which the efficiency of a system is always less than the efficiency of a Carnot system that's operating between the same temperatures of reservoirs. The second Carnot corollary is all reversible power cycles or all Carnot heat engines operating between the same two temperatures have the same efficiency. So as long as the heat engines are reversible, or in other words, they are Carnot engines, and they are operated between the same high temperature reservoir and low temperature reservoir, their efficiencies are all the same. In the case of refrigerator, in which our purpose is to remove heat from low temperature reservoir and to transfer it to high temperature reservoir. The purpose of a heat engine is to convert some of the input heat to work. However, the purpose of or objective of a refrigerator is to remove heat from cold temperature reservoir and to transfer to a high temperature reservoir. It's only possible to by using an external energy. So without this addition of energy into a refrigerator, it's not possible to cool inside the refrigerator, and this is actually the compressor work. So this is the compressor work we have to provide to the refrigerator. So in the case of a refrigerator, we have two types of using modes of a refrigerator or air conditioner, doesn't make any difference. We have two types of coefficient performances. We do not use efficiency in refrigerators because efficiency is always less than 1, whereas the coefficient of performance can be much greater than 1. So in the case of refrigerators, we use coefficient of performance instead of efficiency. The coefficient of performance for a cooler is always output divided by input. So output is the cooling capacity here, and the input is the compressor work. So beta is the coefficient of performance when it's used for cooling. On the other hand, as in the case of household air conditioners, it's possible to use the air conditioner for heating purposes. And when it's used as a heating purpose, then we will use the hot reservoir to provide heat into the room, into the house. So in this case, when it's used as a heater, in which it's called a heat pump, the output is QH, so this is going to be the output when it's used as a heat pump, divided by input. Input is the same. Interesting to see that if you write the sorry, can you hear me? The system has frozen. System had a freezing. Did you hear me recently?
Evet hocam, duyabiliyoruz.
Okay, because it looks like it has frozen, but in any case, so The gamma, which is the coefficient of performance for heat pump, is beta plus 1, meaning that an air conditioner system is always much more efficient when it's used for the heating than cooling. If you write the energy balance here, you will see why it is like this. Because as you can see, according to the energy balance, QC plus W is QH. So if you write these equations, you will see that gamma becomes equal to beta plus 1, meaning that a air conditioning system used as a heat pump, used as a heater, is more energy efficient than using it as a cooling system. When this system converts the PowerPoint slides, some distortion occurs, but in any case, you can see them. In the case of Carnot heat engines and Carnot refrigerators, instead of using the ratio of the heats, so here you are using the ratio of the heat, you can use the ratio of the temperatures. So for a Carnot system, for a reversible system, the ratio of the heat can be written as the ratio of the temperatures. So you can see that it's a reversible cycle, meaning that it's Carnot. So in this case, if you look at this graph, you can have almost an efficiency as high as 1 if you have increased the temperature infinitely. So if, look at this equation, if TH becomes infinitely high, then you get the efficiency to be 1. Or the same thing can happen like this. If T cold becomes infinitely small, then efficiency becomes 1 again. So it means that if we increase the temperature of high temperature reservoir or decrease the low temperature reservoir, it's possible to increase the efficiency of the system. But for practical reasons, it's not possible. For instance, for a power plant or internal combustion engine, because of the material considerations, you cannot increase the temperature higher than 2000 Celsius or 2500 Celsius at most, maybe. So because of the material conditions, material considerations, you have to limit the temperatures below some temperature, for instance, somewhere around here, so that the maximum efficiency for a Carnot system is 60% or maybe 70%. Similarly, for Carnot refrigerators and Carnot heat pumps, we can use the ratio of the temperatures instead of ratio of the heats. So in this case, a Carnot refrigerator using as a cooler is going to have a coefficient of performance as Tc divided by Th minus Tc, and coefficient of performance for a heat pump as Th divided by Th minus Tc. There is an example regarding the use of the theoretical maximum efficiencies versus actual efficiencies. According to the example, it says that an inventor claims that he has a heat engine which provides a work of 4010 kilojoules when the hot reservoir is delivered a heat energy of 1000 kilowatt, while the temperatures of the hot reservoir and the cold reservoir are 500 and 300 respectively. So according to this inventor, we can calculate the efficiency by actual efficiency by work divided by Q input, and it's going to give you an efficiency of 41%. However, if you calculate Carnot efficiency using the temperatures, I'm talking about this equation, then it turns out that the Carnot efficiency is 40%, which means it's not possible, because according to Carnot corollaries, no heat engine can have a higher performance, higher efficiency than a Carnot engine or than a reversible engine. So the claim of this inventor is not correct. Another example says that a refrigerator has a cooling capacity of 8,000 kilojoules per hour, and inside the refrigerator is given as -5 Celsius. You have to convert the temperatures to kelvins. So when you use the temperatures in efficiency calculations or capacity calculations, coefficient of performance calculations, you need to convert them to Kelvin by adding 273 to the Celsius. So you have to do this conversion before you start the calculation. So as you can see, -5 Celsius is converted to Kelvin, and the high temperature reservoir, which is actually the kitchen side, is 22 Celsius, 295 kilojoule, while the compressor of the refrigerator is delivered a work of 3,200 kilojoules per hour. This is the power of the compressor. So it's asking the coefficient of performance of the refrigerator and compare it with the reversible refrigeration cycle operating between this given temperatures. So the COP is always output divided by input. Of course, this is the beta COP, meaning that this is the COP used for the cooling. So beta COP is equal to output, which is the cooling here, cooling energy here, 8,000 divided by the input, which is 3,200. So this is the efficiency of a coefficient of performance of a refrigeration system, actual coefficient of performance. So it turns out that the coefficient of performance of this actual system is 2.5. On the other hand, if you calculate the theoretical coefficient of performance or theoretical coefficient of performance of the reversible system or Carnot system, Carnot refrigerator, is found to be 9.9. As you can see, there's a big difference between the two of them. Actually, by using the two coefficient of performances, you can define a refrigeration efficiency. Refrigeration efficiency is beta divided by beta max, which is the coefficient of performance of a Carnot system, and you will see that it's almost 25%. which is known, but most of the time this is the case because in a refrigeration system there can be many irreversibilities, and because of the irreversibilities, the actual systems can have much lower uh, refrigeration efficiencies uh, the than the theoretical system, the Carnot system. Another example is related to heating a house by using a heat pump. Remember that air conditioners can be used for heaters. So the heater, the air conditioner has a capacity of 600,000 BTUs per day, which is converted to kilowatts as 7.3 kilowatts. So this is the heating capacity of the heat pump. So the heating capacity is 7.3 kilowatts. Internal temperature needs to be held at 21.1 Celsius. This is the temperature of the high temperature reservoir, and external temperature is 273 Kelvin, which is T cold. So you can see that this uh, heat pump is operated between two temperatures, between the temperatures of 273 and 294. And of course, we have to deliver work to it. Otherwise, it's not possible to absorb heat from the low temperature and transfer it to inside the house. So by doing this, we know that the QH, this is just the heat balance, is equal to work addition plus Q cold. So as you can see, we are actually using the energy of the surroundings. And in order to do this, we have to add some external energy, which is the compressor work. So by definition, the coefficient of performance of this heat pump is QH divided by gamma max. Gamma is the coefficient of performance for the theoretical system, for the Carnot system. So the work addition in an actual system is greater than the work addition in a Carnot system because of the irreversibilities. You can write the gamma max in terms of the temperatures, and by calculating the maximum, uh, by calculating necessary compressor work, we find that the compressor work is 0.52 kilowatts. It should be greater than 0.52 kilowatts. It's equal to 0.52. It's an irreversible system, reversible system, but it's greater than this value for an actual system. In one day, you multiply this by 24 hours, and the energy used per day is 20.6 kilowatt hours. Then you multiply it by the price of the electricity, which is dollars per kilowatt hour. Then you get the consumption of electricity in dollars per day. Of course, this is greater than this value because we have used the theoretical uh, coefficient of performance. So as the work must be greater than this value, the electricity bill spent daily must be greater than this value also. So Carnot cycle has four reversible cycles, reversible processes. The reversible processes found in a Carnot cycle, we are talking about Carnot heat engine, are two constant temperature heat addition and two adiabatic compression and expansion. So what happens inside the boiler? It's a heat addition at constant temperature. So as you can see, heat addition takes place at constant temperature. Inside the turbine, expansion is reversible adiabatic, or sometimes we call it isentropic. We will call it isentropic later. So this is another reversible cycle, a reversible process. In the condenser, heat is removed isothermally. It's also reversible, and in pump, the compression is also adiabatic. So adiabatic. So as a result of this, we have four reversible cycles, reversible processes in a Carnot cycle. Two of them are isothermal, and the other two is adiabatic. Adiabatic means that there is no heat exchange with the surrounding. So in the PV diagram, you can see that here we have an adiabatic compression in the pump. As the fluid is compressed, you can see that there is a reduction in the volume. Then heat is added at constant temperature, let's say in the boiler. This was the pump. Then in the turbine, expansion is adiabatic. So turbine work is obtained adiabatically, and in the condenser, we have heat removal at constant temperature again. But in reality, an actual system is a little bit different from this because there are some practical problems of operating a Carnot system. For instance, the pump here must handle a mixture here, fluid plus and liquid plus vapor mixture, but pumps normally can handle only liquid, so this is difficult to obtain. Also, expansion in the turbine is completely inside the mixture zone. In practical applications, it's necessary to expand dry steam or superheated steam through the turbine. So this is not practical either. But having constant temperatures in the boiler and in the condenser is possible. Now we will have a new definition, which is called entropy. Entropy is the most abstract concept in thermodynamics, but we can use it in determining the system performances as well as irreversibilities of the systems. Entropy is actually the uncertainty of a system. So as word, entropy is the uncertainty of a system. If we have zero entropy, the symbol for entropy is zero, so there is no uncertainty. what does it mean to have no uncertainty? For instance, if the temperature is 0 Kelvin, absolute zero, then any molecule will have zero energy. For instance, an air molecule at 0 Kelvin will have no velocity. So we know the location of the air molecule if the temperature is 0 Kelvin, meaning that there is no uncertainty. In this case, the entropy is taken to be zero. According to Clausius equation, inequation, this is an inequation, in a cycle, the integral, boundary integral of dq divided by t must be less than or equal to zero. So this is equal to zero for reversible system and less than zero for irreversible systems. I will explain how to handle the cyclic integral. Here, this symbol says that the integral must be performed around the cycle, and it's called a cyclic integral. This cyclic integral around the cycle is zero if the system is reversible, completely reversible, such as Carnot cycle, and it's less than zero if it's an actual system. So when it becomes zero, we say that it's a reversible system. So the difference between the reversible and irreversible system is a difference of sigma. Sigma is actually called produced entropy. Produced entropy. It has a minus sign in front of it, meaning that the produced entropy can never be negative. It must be positive. So for a real system, if you perform this integral around the cycle, cyclic integral, the integral, the net integral is going to be less than zero, as here. So because sigma is always positive, it means that for a real system, the cyclic integral is going to have a minus value for a real system. Sigma cycle is zero if there are no irreversibilities, such as reversible cycles, Carnot cycles. It's greater than zero. Irreversibility is present, so it's a positive value. Less than zero is not possible, because we know that entropy can only be produced, but the produced entropy is always positive, so it can always be produced. Okay, do you have any questions so far? Okay, let's have a break of 10 minutes then, and we'll be back at 2. So we have already mentioned that entropy is a measure of uncertainty. The higher the entropy, uncertainty. For instance, a substance at 0 Kelvin will have zero entropy because the molecule at 0 Kelvin will have no energy. On the other hand, a solid, for instance, will have a low entropy because solid molecules are rather stationary, they don't move a lot. A liquid will have a higher entropy than a solid because liquid molecules will have some motion, and gas will have the highest entropy because gas molecules can travel at very high speeds. So the uncertainty of a molecule in the gas phase is much higher than the liquid or uh, solid phase. We have understood the meaning, the physical meaning of entropy, but we have to use a mathematical method to define it mathematically also. Suppose that we have a process from A from 1 to B2, which is a reversible process. So there are no irreversibilities during the process of 1 to 2. Another process, B, which is also from 1 to 2, is also reversible, meaning that there are no irreversibilities contained with it. And C is another process which can be reversible or irreversible. If you write the total change of the integral, remember that according to Clausius inequality, the sum of the integrals of dq divided by t must be less than or equal to 0. It's equal to 0 if the processes are irreversible, otherwise it's less than 0. So this is 1 to 2, this is 2 to 1, and it's equal to 0. If we say that the processes are irreversible, there is no production of entropy, so that we can say that the integral of 1 to 2 dq divided by t through the process of A is equal to integral of dq divided by t through the process of 1 to 2 are equal to each other. If they are independent of the paths, this path is different from that path, then it's called a property. A property is is a is a is independent of the path. So because the integral of dq over t from 1 to 2 is equal to dq over 2 from 1 to 2, they are equal to each other, then this equation, this integral, is a property, and this integral is actually called the entropy. So entropy is actually the integral of or differential of dq over t if the process is reversible. So in this case, we can calculate the change of entropy from 1 to 2 or 2 to 1. So the entropy change from 1 to 2 for a reversible cycle is equal to integral of dq over t divided by dq divided by t integrated from 1 to 2. So this will be the change of entropy as the process takes place from 1 to 2. And of course, the process 2 to 1 will have the negative sign of it, so that the sum of the integrals is going to be 0 for a reversible cycle, meaning that there is no entropy production for a reversible cycle. In the vapor tables, there is a column called entropy, which is shown by S. We calculate the entropy exactly the way we calculate the other properties, such as internal energy, specific volume, enthalpy, and so forth. Remember that in the calculation of a property within the mixture zone, we use this equation. So if it's a general property Y in the mixture zone, we calculate it as YF plus the quality of the steam, Y gas minus YF. So it's also applicable to the entropy too. Inside the entropy, inside the mixture zone, we will use this equation to find out the entropy of a substance in mixture zone. If it's superheated, of course, we have to use two independent properties such as pressure and temperature. So by using pressure and temperature, we can use the superheated steam table to find out the value of the entropy in the superheated region. For compressed liquids, the finding the entropy of this compressed liquid is similar to the finding of other properties. In other properties, in the compressed liquid zone, remember that it was approximated as the liquid value at saturation temperature. So this is for compressed liquid. You can replace this Y with internal energy, specific volume, or enthalpy, also with entropy. There are graphical methods to find the entropy values. For instance, this HS diagram is called Mollier diagram, but the Mollier diagrams are not used so frequently anymore. Instead, tables are used. So we're going to use the tables to find out the value for the entropies. As an example, we have state 1 at 3 megapascals, 500 Celsius. State 2 is 0.3 megapascals, and the entropies are the same for state 1 and state 2. So even though the temperatures and the pressures are changing, temperature changed from pressure changed from 3 megapascal to 0.3 megapascal. It says that the entropy does not change. So we use the entropy in the state 1 to be equal to the entropy of the state 2. And we see that this entropy is between these two values. So here you need to use interpolation. If it's not direct in the table, you need to apply interpolation. Or in the mixing zone, we are given internal energy. So it's a mixture of vapor and liquid for R134A. It's a refrigerant. And the internal energy is given as 138.43. And remember that because it's at the mixture zone, it can be calculated from UF plus X times U gas minus UF. This value is given to you so that you can calculate the quality of the mixture. And the same quality of mixture is used to calculate the entropy as well. From the saturation table, you will read the liquid entropy and gas entropy at the given pressure or temperature and calculate the value of the entropy in the mixture, which has a quality of 0.5. Another one says that Water at 200 Celsius, 25 bar is a compressed water. The table gives you the entropy to be 2.32, but we can also take the entropy to be approximately equal to the entropy of the liquid at the given temperature. So it gives you the approximate value of this entropy, which is almost equal to the entropy obtained from the compressed liquid table. So this is from compressed liquid table. If you are given the compressed liquid table, then you can directly use this. Otherwise, you can take the value from saturation table, assuming that it's approximately equal to the entropy of the liquid at saturation temperature, given saturation temperature. So the given saturation temperature is 200. So it gives almost the same value. It's not necessary to use the compressed liquid table. Most of the time, the compressed liquid tables are not available. So in this case, you can assume the property of the compressed liquid to be approximately equal to the property of the liquid, saturated liquid at the given temperature. So we have what are called TDS relations, because remember that for a case of reversible cycle, dq divided by T is called the change in entropy. Or we can write this as dq, which is equal to T times ds. So for a closed system, we know that dq minus dw is du. So you can write this as dq is equal to du plus delta w. According to the compressibility of the liquid fluid, you can write this equation as TdS being equal to du plus pdv, or by using the relationship between the enthalpy and the entropy, enthalpy and the pressure work, you can write the same thing as TdS being equal to dH plus minus VdP. So they are the same things. We do not use the molar basis. So when a property has a bar on it, it's on molar base, but we do not use it. By looking at this, if pressure is constant, then dP is going to be 0. In this case, the entropy change when the pressure is constant is just dH over T. And it happens actually during the condensation or vaporization. Remember that in the condensation and in vaporization, the temperature is constant. And in the saturation table, if you have the enthalpy change between the condensation and table, This enthalpy change divided by the temperature in Kelvin is going to give you the entropy. So the entropy values of the table is actually the same as the calculated entropy table, entropy value by using the enthalpies and temperature. As an example, the entropy from entropy of R134A at 0 Kelvin is found to be the difference of the enthalpy divided by the 0 Celsius, which is 273 Kelvin. It gives you a value of 0.73, which is exactly the same as the table value. So what happens if the substance is an ideal gas? If a substance is ideal gas, then we can use the ideal gas relationship as PV is equal to RT. So in this case, the these DS equations can be written as, for instance, this PV can be written as RDT, sorry. So by using the definition of ideal gas relation, the TS equations can be written as either with the volumes or with the pressures. They are the same things. First of them is CV plus R dV divided by V, or the second one is Cp dt over T minus R dP over P. The entropy change is, of course, the integration of either this one or that one. So the first integral is going to give you the integral of this CV dt t term plus R logarithm of V2 divided by V1. And the second integral is going to give you this integral, which we don't know yet, minus the integral of this is minus R logarithm of P2 over P1. The problem is we don't have any idea what the integrals are, but the tables give the integrals to you. So in the gas tables, in the air tables, there is a column which is called S0. S0 is actually this integral with the lower limit of 0. So S0 means that it's the integral from 0 to, for instance, T1. So this gives you the S0 value for T1. This gives you the S0 value for T2. So the change in the entropy, this integral minus that, or this integral and that, is obtained from the tables by using the S0 values. So we do not need to deal with the integrals anymore. We can use the S0 values given in the tables. Then the first equation or the second equation becomes this one. These are the values obtained from the table. They are the values of the integrals. As an example, an ideal gas, T1 is 300, 1 bar, T2 is 1000, P2 is 3 bar, and we would like to calculate the entropy change from 1 to 2. Then these S0 values are taken from the graph, and we have to calculate this part. So during this process of 300 Kelvin to 1000 Kelvin, we see that entropy has increased by an amount of 0.95. If the specific heats are constant, here we have variable specific heats. That's why we keep them inside the. We have variable specific heats. That's why we keep them inside the integrals. And because we do not know how the specific heat change with the temperature, we cannot integrate it. But the tables give you the integral values. But if you assume that the specific heat is constant in a given temperature range, for instance, the specific heat here, this is the temperature. If the variation is like this, you can take an average specific value for an average temperature. So by using a constant specific heat, then this specific heat goes out of the integral. If you assume that it's constant, it goes out of the integral. By using the specific heats, the entropy change equations becomes this one with the volumes or this one with the pressures. Note that here we use CV, here we use CP, but CV goes with the ratio of the volumes, CP goes with the ratio of the pressures. As an example, it says that the air has an average specific heat between 300 Kelvin and 400 Kelvin. It's given to you. So by using the average specific heat, you can calculate the entropy change during this process. And during the process, the entropy has decreased by 0.17. On the other hand, instead of assuming that the specific heat is constant, but you want to use the air table, in this case, from the table, of course, you need to use the S0 values for T1 and T2. By using the S0 values, you can obtain the entropy change to be almost the same. The difference between two is very small. So assuming an average CP does not change the result too much. But of course, it must be given to you. So it must be provided to you somehow. If the substance is incompressible, meaning that, for instance, if it's liquid, then because it's incompressible, dV is zero, meaning that the volume is constant. So if dV is constant, if it's incompressible, then this term goes to zero. In this case, for an incompressible substance, you have entropy change as an integral of Cp over T. If at the same time C is constant, you have an entropy change for a liquid, for an incompressible substance to be C times logarithm of T2 divided by T1. We said that the entropy production must always be positive, but entropy change can either be negative or positive. If Q is added into the system, if Q positive, then entropy increases. Otherwise, if Q is removed, then entropy change becomes negative. So during this process, you can see that by adding heat to the system, which is the integral under the curve, because the integral under this curve is TdS, which gives you the Q. So the addition of heat will increase the entropy. If you go in the other direction, opposite direction in this process, if you move from state 2 to state 1, meaning that if you remove heat, in this case, the entropy will decrease. The change of entropy can either be positive or negative, but the produced entropy must always be positive. And entropy production is seen in the irreversible systems, whereas we are now dealing with the reversible systems. So in a reversible system, the total heat transfer is T times ds. There's an example regarding this. So in this example, it says that a piston, a cylinder system, has liquid water in the beginning, and by adding heat to the system, this liquid water becomes vapor. So from saturated liquid, it goes to saturated vapor. So we can say that initially it was saturated liquid, then at constant temperature, heat is added, and because of this, entropy has increased from S1 to S2. And the reason why entropy has increased because of the addition of Q. And here the Q is the integral of TdS. So first, let's take a look at what happens when the liquid water is heated. When it's heated, it becomes saturated vapor, meaning that because this is the phase change, it takes place under constant pressure. So piston moves up. As the piston moves up, the work done by the system against surroundings is P times V2 minus V1. As you can see, it's positive, meaning that system does work on the surrounding. So when system does work on the surrounding, it's taken as positive. When surrounding does work on the system, it's taken as negative. So in this case, it's a positive work. So you can see that the work during the expansion of the piston is 170 kilojoules per kilogram. The heat addition under constant temperature is calculated from this integral. If the temperature is constant, you can calculate heat addition by this amount. And actually, the same value could have been obtained from the definition of enthalpy. Remember that if you write the first law for this open closed system, dq minus dw is equal to delta u. So if you combine the terms, you get a situation where dq is equal to dH. This is actually the enthalpy change during the phase change. And you can obtain the same value from the saturated table as the difference of the enthalpy of the liquid and gas, which is the phase change energy during the phase change. So this is the amount of energy required to convert liquid water to saturated vapor, and it's equal to the evaporation energy or phase change energy, or just Hg minus Hf. The energy balance for closed systems must include an entropy balance for closed systems must include an entropy production if the system is irreversible. So by including the irreversibility, you can calculate the total integral of the system as the integral from 1 to 2, which is irreversible, is given to you as irreversible, and the integral from 2 to 1 is reversible. And the sum of the integral will be minus sigma. Sigma is entropy production. So if you use the definition of a reversible cycle entropy change, which is S1 minus S2, so the entropy change for a reversible system from S1 to S2 is dq over T. So you can combine this definition into this equation to get S2 minus S1 is equal to entropy change of the system plus the entropy production within the system. Of course, if the system is reversible, then this becomes zero. Otherwise, you have to include this production of the entropy within the system. Entropy is a property which is independent of the process path, but entropy production is not a property. It depends on the path. So depending on the process, the production of the entropy does change. So it cannot be a property. A property is always independent of the process path. So even though the entropy is a property, the production entropy, sigma, is not a property. As a summary, we can say that the produced entropy, sigma, is greater than zero if there are irreversibilities. It's equal to zero if there are no irreversibilities or the system is reversible. So in the case of a reversible system, the produced entropy is zero. On the other hand, the change of the entropy can be greater than zero. For instance, if Q is added, can be zero if it's adiabatic, or can be less than zero if heat is removed. Entropy change can be anything from 0 to positive or 0 to negative, but entropy production must always be positive. Here there is an example of entropy balance. It says that the substance in this container is delivered or work by a pedal. Meanwhile, some work is added into the system. So due to the addition of the heat, we know that there will be an increase in the entropy of the substance here. And this entropy of the substance is evaluated from dq divided by T, which is the entropy increase during this reservoir. Meanwhile, the reservoir loses this much entropy. If there are many boundaries having different amounts of heat interactions, then the total entropy change of the system is the total heat interaction. Some of them can be positive, some of them can be negative, plus the produced entropy. If the system is irreversible, the produced entropy will be zero. On time basis, per unit time, the first term becomes ds divided by dt, which is entropy change per unit time. Then the second term becomes sum of the q dot, the energy interaction per unit time, divided by t, and sigma dot is the energy production, entropy production per unit time. This is a interesting example, very similar to the previous one, but in this case, instead of providing heat to the system, work is provided to the system. So initially we have the same liquid water, the saturated water at 100 Celsius. So by stirring it, the work energy is added into the system's internal energy, and it becomes a saturated vapor. In this case, of course, during the saturation table, saturated vapor, it expands. But because there is no heat is not added into the system, this integral is not heat. This is not heat. And similarly, this integral is not work. Why? Because this is not heat due to the fact that heat is not being added from the boundary. You can use this equation. If the heat is added from the boundary, there is no heat addition at the boundary. And this one is not work because the expansion of the piston is not due to the increase in the pressure or moving of the piston upwards, but it's because of the expansion of the gas as well as the work added by the pedal here, because the total work here is work of the pedal plus work of the piston, and work of the piston is just PdV, and that's why this is not represented by the work, as well as this is not represented by the heat. The energy balance can be given as delta U plus delta kinetic energy plus delta potential energy is equal to Q minus W. Q is 0, it's given to you. The change in the kinetic and potential energies are 0, so that the work is obtained as the difference of the internal energies. And this internal energy is because of the mixing of the fluid. The energy increase is because of the mixing of the fluid. So that you can find that the work is minus because work is done on the system. That's why it's minus. On the other hand, you can write the change of the entropy as the integral of dq over t from 1 to 2 plus sigma, but because dq is 0, is adiabatic, the first term becomes 0, meaning that the entropy production per unit time is equal to entropy change, and you can calculate it by the entropy values from the table. So the entropy change in this case is because of the entropy production here. This was a previous example, maybe you will remember. In this gearbox, the input power is 60 kilowatt, the output power is 58.8 kilowatts, and the case of the gearbox is losing 1.2 kilowatt. If you note that the total energy is the energy balance can be seen here. dQ minus W per unit time is going to be 0. So if you write 60 minus 58.8, you will find that is equal to 1.2. So this is from the energy balance for a steady system. First, we are going to calculate the entropy change when the boundary of the system is shown. And in the second part, we are extending the boundary of the system to have a temperature of 293. In the first case, the entropy production per unit time is 0 because it's steady state. So it's steady state, so the SDT is 0. Q dot divided by TB plus sigma. So produced entropy is minus Q over TB. The lost heat by the case is given as 1.2. So by using this 1.2, you can calculate the entropy production at the boundary of the system to be 4 times 10 to the minus 3 kilowatts per Kelvin. In the second case, if you consider the system boundary to include the surrounding, you will see that because the surrounding temperature has a lower temperature, the surface of the gearbox is 300, whereas the surrounding is 2.93 kelvins. In this case, you will see that you have a higher entropy production, meaning that here, in the first case, you consider the irreversibilities between the case of the gearbox and the immediate surrounding, which is the surface of the gear case. But in the second one, you have considered also the irreversibilities between the surface of the gearbox and the surrounding. That's why you have an increase in the entropy, even if it's not so big. Entropy, even if it's not so big. So this is because of the inclusion of the other reversibilities. For open systems, as energy balances, we have to consider the entropy transfer due to the mass flows. So in the case of open systems, we have the entropy change due to the heat addition or removal from the system boundaries, the entropy carried into the system, entropy carried out of the system, plus the entropy production per unit time. This is very similar to the equation of the energy, but this is called the entropy rate equation. At the same time, if we write the mass balance, we know that according to mass balance, if it's a steady state system, the mass flow in must be equal to mass flow out. So sum of the MI in must be equal to sum of the ME out. And meanwhile, if you write the uh, energy equation for an open system, because dE dt is zero due to the fact that it's steady state, it's zero because it's steady state. Then in this case, we have zero on the left-hand side, Q dot, which is the heat added or removed per unit time, W dot, work added or removed per unit time, the energy carried by the fluid, the enthalpy of the fluid, the kinetic energy of the fluid, and potential energy of the fluid incoming, minus the total energy of the exiting fluid. And we can also write the first equation. This is exactly the same as this one, so it's just a repetition. If there are only one inlet and one exit, we can find the change of the entropy as entropy production per unit time divided by the mass flow rate. So this is for an open system where there is no Q interaction. So if there is no Q interaction, the entropy change within an open system can be calculated from the entropy production divided by the mass flow rate. Any questions so far? The second law is more abstract than the first law because it has the introduction to entropy. That's why you may need to pay more attention to the subjects of the second law and entropy. Any questions? Okay, let's have another break of 10 minutes. Then we will be back at 3 o'clock. First. In this example, we would like to calculate the entropy produced by this steam turbine during the operation. So let's take a look at the steam turbine. It says that the steam enters the turbine at 30 bars, 400 Celsius, and with a velocity of 160 meters per second. And at the exit, it's 100 Celsius saturated vapor at 100 meters per second, while it's delivering 540 kilojoules per kilogram, and the case of the steam turbine is 350 kelvins. Normally, in the calculations, we most of the time assume that the steam turbine is isentropic, meaning that it's a reversible turbine. If it was a reversible turbine, then we would have a situation at which S1 would be equal to S2S, which is isentropic. But because of the irreversibilities, you see that there's an increase in entropy, and this amount of increase in entropy is actually the entropy that's produced inside the turbine because of the irreversibilities. What kind of irreversibilities can occur inside the turbine? It can be mostly fluid friction. So the friction between the fluid and blade friction. So because of the friction, some of the useful energy potential of the steam has been converted to heat, and because of this, entropy has increased due to the production of the entropy. The mass balance is usual because it's an open system with steady state, so that mass coming in must be equal to mass going out. This is the mass equation. And entropy balance at steady state, the entropy change due to the heat interchange at the boundary, the entropy carried by the incoming fluid, entropy carried away by the outgoing fluid, plus entropy generated within the system. Because we have only one M, we can write the entropy carried, net entropy carried in and or out of the system as M S1 minus S2. And from here, you can calculate the creation of entropy to be Q divided by M T boundary with a minus sign plus entropy change. We don't have any information regarding the Q yet, so we can calculate the Q by using the energy balance for the open systems. As you remember, energy balance for the open systems must be equal to Q dot is equal to W, the change of the enthalpy and change of the kinetic energies. The potential energy change is zero. We do not need to worry about it, but we have to take into account the kinetic energy change because it's given. So this much energy change is due to the kinetic energy, and this is the enthalpy change according to the given values. At the inlet, it was a steam at 30 bars 400 kelvins, and at the exit it says that it's a saturated vapor at 100 Celsius. So for this first one, you're going to use the superheat steam table, and for the exit, you're going to use the saturated table. So by using the superheated and saturated tables, you can calculate or read the values of the enthalpies. So eventually, you can find the Q, which is minus 22 kelvins, kilojoules per Kelvin kilogram. It means that at the operation, the turbine case is losing some heat because the turbine case is hotter than the surrounding. You can see that it has a temperature of 250, and most possibly the surrounding is, let's say, 300 or something. So there is a heat loss from the turbine case, and this heat loss is calculated to be minus 22.6. So if you include this in the calculation of the entropy change or entropy generation, as you can see, because heat is lost, the entropy change due to the heat loss is negative. So this is reducing the amount of entropy production. This is interesting. This term causes an amount of entropy generation because of this minus sign. However, during the process, there is a positive entropy increase, but the net change of the entropy is positive again. This is another interesting example. An inventor says that he has come up with a device which can obtain cold air without any refrigeration system. According to the system, he says that at the inlet, he has a high pressure air, which is divided into two branches, and one of the branch will have a lower temperature, higher temperature, and the other one is going to have a higher temperature. So what happens is, because of the restrictions inside, because of the expansion and restrictions inside, even though the total change of the energy will be the same, or energy is conserved, we will see that due to the change of the entropy, the inventor may be right. But in order for the inventor to be right, we have to check three things. The mass conservation equation must be checked. The first law must be checked, which is the energy conservation. And the second law must be checked, which is the entropy balance. If these are all found to be correct, then the inventor is right. So this kind of invention can work, which has high pressure at the inlet, and as it expanded to uh, low pressures, from one side you get a high temperature air, whereas on the other side you get a very low temperature air. We have the SI values of the problem. At the inlet we have 5.1 atmosphere. One of the inlets has 1 atmosphere. The one of the outlets has 1 atmosphere. The other outlet has 1 atmosphere also. But one of the exits has 200, 353 kelvins, whereas the other exit has 255 kelvins, which is actually a very low temperature. It's like minus 20 Celsius. So by using this special device, even though at the inlet you have 294 Celsius, 94 kelvins, exit temperature of minus 20 can be obtained according to the invention, but you need to check whether the invention is theoretically possible. In order to do this, you have to check the mass conservation, the first law, the conservation of mass, of energy, and second law, the entropy balance. So let's check if they're correct. The first one is mass balance, which is okay. The second one is the energy balance. Because this is a steady state system, dE dt is 0. You don't have any Q interaction. You don't have any work interaction. You have kinetic and potential energy changes to 0, so that you are left with the enthalpy flows in and out of the system. So by combining, you need to check this, of course, by using the mass flow rates in M1, M2, and M3. You go through the calculations by using enthalpy is equal to Cp times T. And you will see that it becomes 0 on the both sides, meaning that first law is satisfied. How about the second law? For the second law, we have to check the entropy balance. It's again steady state, so that entropy change per unit time is 0. The device is well insulated, so there is no heat interaction on the boundary. dQ is 0. You have the entropy coming inside, entropies going outside by the mass flow, then entropy generated. So if you write the masses in terms of each other. By the way, the inventor says that 60% passes from one side, 40% passes through the other side. So the flow of the air is divided by 40 by 60. So you use the 40 and 60 ratios of the flow here also, and in the calculation of the entropy balance also. So accordingly, when you calculate the entropy balance with DS equations, remember that this is an ideal gas, so you can use the DS equations for ideal gas. So this is the first term, the second term. Let's take a look at the equation in SI terms. Then you see that the production of the entropy has a positive value. So as long as sigma is positive, the entropy production is positive, we can say that this system is feasible. It's theoretically possible because the entropy production is positive, so that the second law is also satisfied. So this strange device is actually capable of cooling, and the cooling amount is actually substantial. So it can cool the air as low as -20, and this is actually used in the industry. Most of the time in our calculations, we can assume some devices like turbines or compressors can be taken as isentropic devices. Isentropic devices are both adiabatic and reversible. So isentropic is actually both adiabatic, meaning that there is no heat interaction, plus reversible. So most of the time, we assume that devices such as turbines and compressors can be taken as adiabatic, adiabatic plus reversible or isentropic. When a device is isentropic, entropy is constant. So in this case, look at this graph. The fluid is expanding from P1 pressure, T1 temperature to P2 pressure, P2 temperature to P3 pressure, T3 temperature, and all of them occurs at constant entropy. So this process and this process are actually isentropic processes because entropy is constant. In the case of ideal gas, if entropy is constant, then it means the change of entropy is zero. So this is S2 minus S1. So in the case of isentropic process, this left-hand side becomes zero. And remember that the entropy change for the ideal gases can be calculated from the difference of the S0 values minus this pressure term, or sometimes you can use the term with the volumes. If you use the term with the pressures, then you can find the pressure after the expansion as the first expansion and the first pressure times exponent meaning e to this value. And the ratio of the P2 divided by P1 is actually called PR. It's called relative pressure. And also, there is also a relative volume. So relative volume is V2 over V1. So we have PR, relative pressure, and VR, relative volume. And these are actually the columns of the air table. For the case of specific heats, in here, the specific heats are not constant. That's why we have to use the tables. But if you use constant specific heats, then the integral becomes this one or that one. C is constant. When C is constant, everything becomes much easier. For instance, CP can be written in terms of the K and R, and CV also can be written as K and R. K as the ratio of the specific heats. So in the case of constant specific heats, you have the isentropic relationships. So these are the isentropic relationships. You don't have to memorize them, but especially in the cycles of internal combustion engines, we are going to use them a lot. So these are the isentropic relationships. If the specific heats are constant. There's an example regarding this. So in a process, air is compressed from 1 atmosphere to some other pressure, and initially the temperature was, let me tell it to you in SI system. So initially the air was 300 kelvins, and it's compressed to 644 kelvins. So by using the compression, by using the isentropic compression, because as you can see, this is isentropic compression. S1 is equal to S2. First, we are going to use the table to find out the final pressure. So in order to find the final pressure, we need to go to table from T1. We go to the table to find P1, PR1, sorry. And from T2, we get PR2. And because the ratio of them is equal to the ratio of the actual pressures, we can find the exit pressure of the compressor. Let's say this is a compressor, most possibly because the pressure is increasing. So for the case of gases with varying CPs or CVs, CP not constant, you need to use the tables. So in this case, the exit pressure is found to be 15.2528 atmosphere. So it's compressed from 1 atmosphere to 15.28 atmosphere. Now, as the second part of this problem, we are going to use constant specific heats, and we can take the specific heat for this average temperature between 300 and 644. For the average temperature, we can go to the tables and find the values of K first. So this is the CP at the average temperature, and this is the CV at the average temperature. So first we find the K values, which is close to 1.4, most of the time the case. Then, by using the relationship in constant specific heats, this relationship, so these relationships, we can calculate the final temperature to be 15.25, which is close enough to this value. So as long as you pick a correct average constant specific heat, the calculation of the isentropic calculations are very close to the calculations obtained from the tables of the air, which have varying specific heats. Other devices such as nozzles, turbines, we may have isentropic or non-isentropic situations. For instance, in the case of a turbine, normally we can assume that the expansion is isentropic. So in here, this represents isentropic expansion. It has 2s, meaning that the entropy does not change. S1 is equal to S2. But in reality, because of the irreversibilities within the turbine, mostly the fluid friction between the fluid and turbine blades, the entropy increases. This is because of the production of entropy. So this much of entropy has been produced because of the entropy production. And because of this, you can see that the work output of the turbine has reduced. Normally, the work output of the turbine can be calculated from this for an isentropic situation. But in real situation, it has reduced by this amount. So you can write an efficiency of a turbine saying that the turbine's isentropic efficiency is the actual turbine output, which is H2 minus H2, divided by isentropic turbine output, which is H1 minus H2S. So this is H1 minus H2 divided by H1 minus H2S. So due to the H2S, so due to the irreversibilities, this is less than 1, meaning that because of the irreversibilities inside the turbine, some of the work potential has been lost to the irreversibilities. For the nozzles, you can use the nozzle efficiency as the ratio of the inlet and exit kinetic energies. So the kinetic energy at the exit divided by the kinetic energy for the isentropic case will give you the nozzle efficiency. But most of the time, a well-designed nozzle can have an efficiency of isentropic efficiency of 95%. So most of the time, a nozzle can be taken as an isentropic device. For pumps and compressors, the situation is a little bit different because for pumps and compressors, the objective is to increase the pressure. So if the compression is isentropic, the addition of the work to the compressor of the pump is this much. So this one is actual work. Sorry, the addition of the isentropic work. And in reality, because we have to overcome the irreversibilities, the amount of work to be added to compressor or the pump must be larger. So this one was the isentropic one, which is less than the actual one. So in the case of a pump or compressor, the calculation of the efficiency is different from the turbine. In this case, it's WS divided by W actual. So this is for compressor or pump, whereas it was the other way around. It was actual divided by isentropic. So turbine's isentropic efficiency is actual turbine work divided by the isentropic turbine work, because it delivers less work in actual than in isentropic, and in pump or compressor, it requires more work than isentropic case. So it requires more work than isentropic case. So here we are going to calculate the isentropic efficiency of a turbine. Normally, if the fluid, let's say steam, has expanded isentropically, we have the same entropy. However, due to the irreversibilities within the turbine, the exit enthalpy is greater than the isentropic enthalpy, meaning that it delivers less work in actual case than the isentropic case. So the isentropic efficiency of the turbine is actual turbine work delivered divided by the isentropic turbine work. So by multiplying the isentropic work by the efficiency, we get actual work. So actual work is found to be less than the isentropic work. This difference is the isentropic work, and the actual work is less than this isentropic work. And as I said, the reason why it delivers less than the isentropic is because of the production of entropy. Production of entropy means that due to the irreversibilities, we have lost some of the work potential, and it's mainly the fluid friction between the steam and the turbine blades. Again, another example in which we are given a turbine with an inlet of 3 bars, 390 kelvins, and the work obtained from the turbine is 74 kilojoules, and exit pressure is 1 bar. So normally, if the turbine had an isentropic expansion, then S1 would be equal to S2S, and it would deliver this much energy, WS, but due to the irreversibilities, the entropy increases. As you can see, the entropy increases. The increased amount is entropy produced, and actual work is less than the isentropic work. So this is the isentropic work, H1 minus H2S, and we can calculate it by using the air table. This is an air compressor, air turbine, sorry. So by using the air table, the PR values, we can calculate the work produced by this turbine isentropically. So the isentropic work is 105. However, in the beginning of the problem, it says that the actual work that the turbine produces is 74. So the actual divided by the isentropic will give you the isentropic efficiency. As you can see, it's the value less than 100%. So what happens during an internal reversible process if there is a heat transfer on the boundary? If there is a heat transfer on the boundary, so you can see that the temperature is increasing, so that entropy is increasing too. So it means if there is a heat input to the system, this will cause an increase in the entropy. On the other hand, if heat is removed, we know that the entropy will be reduced also. So we can write the entropy production, entropy balance equation for a steady state system as this. If it's a steady reversible system, the entropy production will be zero, so that the entropy change due to the heat addition will be only this. This is for reversible system, where sigma is zero. So we can calculate the Q from the change of the entropy. On the other hand, if you write the energy equation for an open system, the work in this open system can be written in terms of heat, enthalpy, kinetic energy change, and potential energy change. And heat from this equation can be written as TdS. So instead of writing this, it can be written as TdS. So because we have the TdS equations as dH minus VdP, it can be replaced into the equation so that the work for an open system, for a reversible open system, is the integral of minus VdP, kinetic and potential energy changes. If kinetic and potential energy changes are negligible, then for an open system, the work is obtained is minus VdP. This is interesting because remember that for a closed system, the work is calculated by PDV, for instance, in the case of a piston cylinder system, but in open systems, it's completely different. W is minus VdP. So this is the difference of the work for a closed system and open system. If it's a pump which pumps a liquid like a water pump, then it means that V is constant for liquids. In this case, the work for a pump is calculated from minus V, this is constant, times the change in the pressure. And most of the time, this is what you're going to use for the power calculation of a pump. The power calculation of a pump is always the specific volume times the pressure change. How about the situation in polytropic processes? Remember that polytropic process is when the exponent is N, and N depends on the type of gas or type of process. In the case of polytropic processes where we have a relationship between the pressure and the volume as this is polytropic process. So for an open system, the work for a polytropic system is calculated by the integral of minus VdP. So because PV to the n is constant, you can write the P, V in terms of P. You can write the P in terms of P. So when you do this and perform the integral, this will be the work in a polytropic process when n is different from 1. And in the case of polytropic exponent is 1, the work in an open system is this. If it's an ideal gas, then in this case, we can use the ideal gas relationship, and we can rewrite the calculations of the work. So in place of using the PVs here or PVs there, you can use the temperatures because it's an ideal gas. By using the temperatures, we can calculate the work in an open system as minus nr n minus 1 times temperature difference, or we can write the same equation with pressures as well. In the case of n is equal 1, it becomes something different. As an example here, air is compressed from 1 bar, so air is compressed from 1 bar to 5 bars. During the compression, temperature increases to 425 kelvins. And it says it's a polytropic process with a polytropic exponent of 1.5, so its PV to the 1.5 is constant. So by using the polytropic process relations, we can find the exit temperature T2 divided by T1 is equal to the pressure ratios to the n-1 divided by n, so that the exit temperature from the compressor is found to be 425 Kelvin. So Because this is an open system with a polytropic process, the work in the polytropic process can be found from this equation. Note that it gives you an work less than 0 because work is done on the system. That's why it's minus. On the other hand, you can write the energy equation by Q minus W is equal to H2 minus H1. From here, you can calculate the Q. And according to this, during the compression, there is a heat loss to the environment. So you can see that this minus sign says that it's a heat loss. So as the compression takes place, there is some heat loss to the surrounding, which is found from the energy balance. In the beginning, we didn't know it, but according to the calculations, we see that during the compression, as we deliver energy to the system, to the compressor, as the compression takes place, the compressor loses some heat. It's mostly the heat lost by the body of the compressor, or maybe it's a compressor with water cooling, we don't know. But we see that there is a heat loss to the surrounding. So by using the total work of the system, it's the work due to the compression plus the change in the kinetic energy plus change in the potential energy. This is with internal reversible system, meaning that there is no change in the generation of the entropy. There are no irreversibilities. That's why we do not have any change in the internal energy. This we know from the fact that it's internally reversible. So by considering the losses due to the reversibilities, the losses due to the reversibilities can be included in this term, H loss. This is the irreversibility type of losses, such as friction, especially fluid friction. So you can see that in the case of without any friction, we will have the total energy at the inlet is equal to the total energy at the exit, which is actually called Bernoulli equation. But without the assumption that there is no irreversibilities and there is some heat term in work term in it. So with the inclusion of work term and heat losses, the head losses or friction losses due to irreversibilities, this equation can be written with the total energy at the inlet is equal to total energy at the exit plus work added to the system plus energy losses due to the irreversibilities. So for a steady state system, we can write the whole thing by bringing similar terms together as work, then net pressure work, the net change of kinetic energy, the net change of potential energy, minus the losses from the system. And also we have the energy equation. According to the energy equation for a steady state system, this is d over dt, and for a steady state system it's 0. So according to the steady state open system energy balance, the net work per unit time minus the net work, the net Q per unit time minus the net work per unit time. This term includes the internal energy change and the energy due to the pressure change, the change due to the kinetic energy, and change due to the potential energy. If we subtract the two equations from each other, we get something as 0 is equal to QCV minus the change in the internal energy plus the losses due to the irreversibilities, which says time rate of change of the internal energy contained in the system is equal to time rate of change of the internal energy being transferred at time t minus time rate of energy transferred out of the system at time t plus rate of internal energy being generated within the system, which is this one. So as you can see, due to the friction or other irreversibilities processes, such as heating by an electrical resistance, we get this term, this final term, as a friction heating or heating due to the electrical resistance. Any questions? Okay, so see you next week.